Welcome back to the virtual classroom of Chem-based School of Chemistry. This is the very first study pack 1.1 where we discuss about the chemical formulae, and how to write the chemical formulae, and the main concept of this unit is about the ionic equations. So the first part of the TUT, the chemical formulae, is what I've discussed O levels as well, how to write chemical formulas. I'm not going to spend much time on that. I'm going to just quickly go through that, explaining the difference between a complex formula and a simple formula. And then I'm going to spend more time on ionic equations. Now, when it comes to chemical formulae, which is the plural of formula, the most important thing is we don't memorize formulas. We don't memorize anything. We just derive the formula with the help of the valency of the elements. Now we know what is valency, right? The valency of an element is defined as the positive or the negative charge acquired by an atom by losing or by gaining electrons. So if we take, for example, the periodic table, by analyzing the group number of the elements in the periodic table, we can easily predict the valency. We know the group 1 has a valency of 1, which is +1, group +2, and these elements which are in the D block, these elements, they show multivalency, except for, of course, the scandium, I think, is exceptional. Other than that, other elements of this area shows multivalency, meaning more than one valency. So you cannot identify their valency directly. Group 3 is +3, group 4 is ±4, group 5 is -3, group 6 is -2, group 7 is -1, and the group 8 is, the valence is 0, because they don't lose or gain electrons, because they have a completely filled outer shell of electrons. As a result, they don't lose or gain electrons. That's the reason why the valency of this group 8, is 0. And that's also the reason why we call the group, the inert gas group, as a 0th group. There are a few elements in the group 4 as well, and other groups, which shows multivalencies. Like tin, lead, these elements at the bottom, they also show multivalency, right? Writing the formula, you need to work out the valence of the elements first. Let's see how to write the formula, right? When you're writing simple formula, you have to work out the valency of elements. And again, the periodic table is given at the exam, so you have to simply use the periodic table and cross the valencies and work out the formula. For example, if I tell you to write the formula of aluminium, I know all of you have done O levels, but you know, the thing is, when you come to my A level class, I assume chemistry knowledge is 0, right? There where I start all the chapters. So even if I got A star or very high grade, I'm sorry about that. I had to repeat from the very basics, because the reason is the unit 1, the chapter, unit 1 especially, the entire unit 1 is the backbone of your entire A levels. Now I know A2 students, when I tell you to write the formula of ammonium phosphate, many can't write. Many can't write, right? Because remember, because of their foundation is not strong. So you notice I go in detail in the foundation chapters, because I want your foundation to be strong. When your foundation is strong, your backbone is strong, your advanced chemistry will be perfect, right? So I need to make sure this foundation chapter is done properly, because I don't know how many of you know the difference between ate, and ide. Why we say sodium, aluminium oxide? Why don't we say aluminium oxygen, right? All these minute details you need to know, right? Because if you can't write a formula, you know, it's like you're doing A2 maths or A-level maths without knowing addition. You don't know 1 + 1 is 2, but you're going to do the A-level maths. You know what you have to face. So similar situation you have to face when you can't write a formula, right? So when it comes to aluminium oxide, right, shortly I'll explain why is oxide, not oxide, or not oxide, or not oxygen. Why we say oxide, I'll explain to you shortly. The first step would be to write the symbol of the element. So aluminium is Al, oxygen is O. When you're writing the symbol of elements, remember, if an element contains more than one letter, the second letter should be always lowercase. You should never write chlorine like this. The second letter should be always lowercase, right? And then what you do is you write the valencies. Aluminium is group 3 plus 3. Oxygen is group 6 minus 2, and you cross the valencies. The valency of oxygen goes to aluminium, and the valency of aluminium goes to oxygen. This will be the formula of the aluminium oxide. So why we call it as oxide? Why not aluminium oxygen? Why not sodium chlorine? Why we say sodium chloride? Why we say potassium sulfate, sometimes sulfite, sometimes you end with ate, sometimes you end with ite, sometimes you end with ide. What's going on here? Why the different ways to end the name? Remember, the rule is if you're ending the name with an element. When I say element, the elements which is found in the periodic table, simple elements, right? You end with the suffix "ide." But if you're ending the name with a complex ion, when I say complex ion, for example, you have this nitrite, nitrate, sulfate, sulfite, you can see these complex ions here. Then you have to either use ate or ite. Suffix ate or ite. I'll explain shortly where to use ate, where to use ite, right? Except for, of course, there's one exception to that rule, hydroxide. We don't say, even though it's a complex ion, we don't say as hydroxate or hydroxide. It's not easy upon the tongue, so it's only exceptional for that. We say hydroxide, right? So if it's ide, that means you are ending with the element, right? Okay, so sometimes some elements have more than one valency. In that case, the valency will be given in capital Roman numerals in brackets. For example, you say copper 1 oxide. Copper is +1, oxygen is -2. You cross the valencies. Copper 1 oxide. Why I give the copper in capital Roman numerals in brackets? Because copper is an element which has more than one oxidation number, right? More than one oxidation number. It's a multi-oxidation element. So when you have multi-oxidation elements, you have to indicate the valency in capital Roman numerals. Sometimes you get situations like this. For example, lead 4 oxide, because lead is also a multivalency element, right? So you have lead Pb +4, oxygen -2. You cross the valencies, you get Pb2O4, which you can simplify as PbO2. Remember, the valencies which you cross, you can simplify them, right? Only the valencies, copper 2 oxide, Cu +2, O -2, you cross the valencies, Cu2O2, which is CuO. Clear? So when you can, the valencies, if you can simplify this valency, you should simplify. But when you have radicals, be careful. That means radical is a combination of more than one element with the overall charge. Say, for example, if I say sodium sulfate, right? Sodium is +1, sulfate is -2. So when you cross the valence, you get the formula like this. So you cannot simplify this and say sodium sulfate is NaSO2. This is wrong. You can't simplify the part of the formula. You can only simplify what you cross, the valencies. Only valencies can be simplified. Remember, you cannot simplify part of the formula of the complex ion, right? I hope it's clear. You can copy these 4 examples. Well, let me know once you're done. Those who are joining for the first time, your microphones are muted from my end to prevent the background noise. If you need to speak to me, just let me know in the chat column. I'll unmute your microphone. You can present your question over voice. If not, you can type your question in the chat column. So always the capital Roman numerals are used, especially when you have elements with multi-oxidation states, meaning more than one oxidation state. In that case, you have to indicate the oxidation state in capital Roman numerals in brackets. Done. Right, so we know why the valency of the noble gas is 0, because they have a completely filled outermost shell of electrons. So not always you get elements combining to form a compound. Sometimes you get element and a complex ion. Complex ions are ions which has more than one element with the overall charge, right? As for the valencies of the elements, you're not supposed to memorize them. You can derive the valencies with the help of the periodic table. Suppose if it is a multivalence element, then again the valence will be mentioned in capital Roman numerals in brackets. As for hydrogen, it has one electron in the outermost shell, so you can lose that one electron and form hydrogen ion, which is +1, or it can gain an electron and form the hydride ion. H plus is the hydrogen ion, and H minus is the hydride ion. So hydrogen can be either +1 or -1. Carbon +4 or -4. Nitrogen group -3. Again, don't memorize any of these valencies of elements. Valence will be given in capital Roman numeral. Group 1 +1. If it's a multivalency, valence will be given. If it's a normal element, on the periodic table. Aluminium +3, silicon +4 or -4. Phosphorus is -3. You got the sulfur is -2, chlorine -1, potassium +1, manganese is +2 or +7. Again, when it comes to manganese, the valence will be given in capital Roman numerals. Ferrous and ferric, Fe2+ and Fe3+, right? We say Fe2+, ferrous, and with US, suffix us means a lower oxidation state. We end with suffix ic for the high oxidation state. I'm just going to go in briefly on all this because these are all done for your O levels. So I'm going to go in a little bit fast because of the reason we have done all this before, right? If you want, any of you need further explanation, let me know. So this is us, we say ferrous, cuprous, cupric, and cuprous, cupric, ferrous, ferric. So ferric, we use the suffix ic when the oxidation number is higher. So cobalt is 2+. We have cobalt +2. That's a common one. +1, +2. Zinc is +2. Zinc is not a multi-oxidation state element. It is not, even though it's in the D block. This is the valency of iron. Iodine -1. Lead +2 or +4. Mercury is +2 and silver is +1. Right? Please copy the valencies of these elements. Let's look at the valency of the radicals. which has a combination of more than one element with the overall charge. So I prefer without saying radicals sometimes, because we have organic radicals as well. Organic radicals are different to the inorganic radicals, but anyway, the definition of radicals is different there. So I can call this as complex ions as well, in order to avoid the confusion. Because in organic chemistry, we define radicals as species which is formed as a result of the homolytic bond fission. So hydroxide is -1, nitrite -1, nitrate -1, sulfite -2, sulfate -2, ammonium +1, carbonate -2, bicarbonate and bisulfite and bisulfate. All of these are -1. Phosphate is -3, manganate is -1, chlorate, chlorate 1, chlorate 5 is -1, and then you have vanadate we say, chromate and chromate, all the isolate, all these are -2. Now the question arises, how do we know the valencies of radicals of the complex ions? For elements we know, right? So when it comes to radicals, about 16, 17 radicals, about 12 or 13 you already know from your O levels, right? You already know the valencies of radicals from your O levels. But you have to remember there is no shortcuts for certain radicals you can work out. I'm going to explain how to do that. But most of these basic radicals, which you have studied for O levels, up to what permanganate you know from your O levels. You see the A level, only little bit you remember. So for this, you have to remember the name and the valencies of these complex ions. Some of it you can work out, right? For example, hydrogen carbonate. Now, hydrogen carbonate is also referred to as bicarbonate shortly. So we know carbonate is -2. This part is -2. Hydrogen is +1. So +1 and -2 is -1. Right? Some of it you can calculate, not all. Right? And hydrogen sulfide, which is also referred to as bisulfide, we know sulfide part is -2 and hydrogen is +1. You know sulfide is -2 from here. So therefore, a -2 and +1 is -1, right? Okay. Likewise, hydrogen sulfate, bisulfate, right? Phosphate is -3. Manganate 7. Now, what's this 7 here, right? Manganate 7, right? The manganate 7 refers to the oxidation state of manganesia. You can work out, right? For example, permanganate, MnO4. Manganate 7, that means oxidation state of manganese is +7. Always the first element, the metal, it's positive. Oxidation state of the first element, metal, is positive. This is -8, right? So +7 and -8 is -1. So you can work out chlorate 1. That means chlorine is +1 here. Chlorine can take +1. It can lose 1 electron. Generally, it's -1, but it can be +1 as well. And oxygen, we know it's -2. +1 and -2 is -1.